fact that the actual computers, so people are in different geographical places. So when let's take you have this people like we here, and each of us goes to a different place and has a mobile phone and can call other people, but there are only two people communications. Turns out the bad guys then can say different things to different people, and the consensus becomes really harder. The same really simple voting problem becomes really harder. So the problem, this Byzantine generals problem, which appeared in mathematics in 1982, there was a work of a guy at MIT that did this. So how do you make sure that multiple entities which are separated by distance can actually have agreement? So agreement of people in the same room is trivial. This one turns out to be pretty hard. So that's also, sometimes people say it's a Byzantine general problem. Generals need to decide attack or retreat. If all of them attack, all of them retreat, it's fine. If some attack, some retreat, it's a problem. And they just have like people on horses, just go and pass messages, and they need to actually come to the agreement. This turns to be a pretty hard problem. And there were many different algorithms in academia, starting from 83, and the algorithms kept on improving. Now, it works pretty well. The current algorithms work pretty well. In particular, we are using an algorithm from a group in France, actually, at University of Nantes in France. Here's the guy. He invented this binary consensus, which works very well. And let's look how a single binary consensus works. When you decide yes or no a single way, a single time, you will see that this actually works really fast. You will just see it working in a second. That's it. Let me do it again. And wait, so this is a single binary consensus. That's it. But that's actually a progression of academia. From academia, it used to be much harder, but now it's easy. So then what turns out, that once you have this, you can select the winning proposal by doing multiple binary consensuses. You have multi-valued consensus. You need to select one proposal out of many. Turns out it can be split into several iterations of this thing I've just shown, the binary consensus, and then you can safely and securely select the winner, and the winner will be the same on all computers, on all nodes. And then, once you have the winner, so that was this phase, just finalize. As I mentioned, they need to sign, and some of them need to also download the proposal, but because the threshold signature means that 2/3 of the guy already had the proposal at the proposal phase. The proposal is widely distributed, and everything is fine. So these are the mathematical steps. And you see, actually, the steps are not so hard. After this, you can just go to phase number 1. So again, for you guys to remember, maybe you to use at a party today, just to talk about consensus, several phases. Proposal phase. During the proposal phase, it has to be unique, and it has to be widely distributed. And then the consensus phase, where all of them decide which one wins. Okay, so that's it. I think that's the end of my talk. I'm just going to talk about Scale a little bit more. Again, Scale is a network of blockchains, which just plugs into Ethereum. We don't have our like own layer 1 network, just plugs into Ethereum, and it's Web3. So you can take Uber, run it on Scale. You can take Airbnb, run it on Scale. And the way we did this, we took Ethereum virtual machine, and we added file storage, we added some other things, we added web server. So it actually looks very much like a web server. But you can still program in Solidity. You can use Truffle, whatever tools you have. And so it's Ethereum compatible, fully Ethereum native network, which is Web3. And you all guys are welcome to try Scale. Last thing I wanted to say is that we're also planning something which we call a pre-Y Combinator camp. It's going to be a kind of a Burning Man style camp in Utah, in a secluded location in the mountains. We will bring together Scale engineers and people that want to do startups. It's pre-Y Combinator, so if you have an idea, that's great, but you can come without idea, and we pay for it. The way to apply, you send a Twitter message to me or to any other like Scale members on Twitter, and you send a 2-minute video about yourself, and then you can come to Utah, and hopefully at the end of this camp, People will be submitting applications to Y Combinator. We'll also have really famous VCs, Floodgate Capital, Signia Ventures, many other VCs participating in the camp. So you'll also be able to talk to VCs. So come to the camp, apply. Thank you, and now I'll take your question, guys. Yeah, guys, I forgot. My Twitter is, just search for me on Twitter, is just search for Konstantin Kladko. My name, again, just search for it on Twitter, and it will be really easy. You're all computer scientists, so here it is. Here's my name. And if you find me and follow me, then you can apply for the camp. Here's my name, Konstantin Kladko. Just search it on Twitter. You'll find it. Questions? Any other? Anything that you didn't understand? Okay.
Just like a super basic question, I'm sorry. I'm very new to blockchain. So what's the difference between proof of work and proof of scale?
So proof of work means that the consensus, we discussed this consensus. The consensus and proof of work is really simple. Many guys do number crunching, and when they do this number crunching, one of them, it's like a lottery. So one of them, you do number crunching, you crunch and crunch and crunch, and at some point, you win this lottery. You have the solution, but to find the solution, you need number crunching. Every time you try, you actually play this lottery. So when you win the lottery, you become the winner of the consensus. So we discussed here that there are multiple block proposals, and you need to decide who is the winner of this multi-valued consensus. And in proof of work, the winner is the guy who did lots of number crunching and won the lottery. In proof of stake, there's no number crunching, there's no lottery. So there are mathematical algorithms I discussed. They actually can select the winner without having to crunch numbers. You've seen the photo of the guy in France. He designed the algorithm we use. So these algorithms are great because they allow to save energy and not do this number crunching. The problem is they are actually complex. They take time to code. So you guys, if any of you guys want to use our algorithms, they're all open source on GitHub. You can take them, use them, and they're actually pretty stable now. We've been developing them for like 3 years now. So they're pretty stable, they have little bugs, and actually they're really good to use at this moment. So use them if you want. Thank you. Yeah.
So you mentioned that for your algorithm, the keys for the threshold signature need to be generated in advance before the genesis of the blockchain. Does that mean that this algorithm is not really suitable for public blockchains, so that new validators cannot join the validator set?
Yeah, this is a really good question. So in this algorithm, you can also have an iterative phase where you have a new guy. It's like hockey, right? If any of you guys are from Canada here. In hockey, you have 5 guys, they jump out of the game, and the other 5 guys. So what you're asking is exactly this, right? Some people joining and leaving the network. Turns out you can actually have this iterative phase in DKG where the new guy got there, and then for the new guy, there's a smaller algorithm to join. Frankly, because we have version 1, we don't have it yet, but we are planning to implement it. Currently in our system, every time a guy joins, we redo this DKG. But in the future, there are iterative algorithms that allow you not to do it, a smarter way for the guy to join. Another thing, a really important thing, I was talking at ENS conference meeting yesterday, and another great thing that this algorithm allow to do is something which is called threshold encryption. It's a collective way to decrypt things. I am sending a transaction, it's encrypted. It actually goes into blockchain in an encrypted way. And only after that, if it is in blockchain, it gets decrypted collectively. And it's interesting that you can prove that it totally eliminates something which is called minor value extraction or front running. Basically, if your transaction is encrypted when you send it, then the bad guys don't know what's inside, they can't front run you. So Uniswap that runs on a blockchain, which does this threshold encryption, is provably secure against front running. So you can take Solidity code for Uniswap, run it on a blockchain that has threshold encryption, it will have zero, probably zero front running, probably zero MVV, and that's something which we're working on now at scale, to add this feature for threshold encryption, because once we have it, it magically removes front running and MVV, so you take pretty much any DeFi application, you run it on a blockchain with threshold encryption, and it becomes free of MVV and free of front running. So it's also, so these things, these threshold signatures and threshold encryption really turn out to be magic things that solve lots of problems by a single mathematical object, essentially. And any other question, guys? Okay, I would like to thank you so much. Please go to our GitHub, take our code, fork it, use it, steal it. Also go to us on Twitter and apply for the camp. Thank you. Thanks for coming.